So I want to start out this screencast. This is for the week 5 class, and just talking about my experiences with the mapping electric field lines um, and mapping potential, I guess, uh, activity. What I chose to do is we have some kits at our school through science first, and if you can see these, it's that resistive paper, I guess resistive conductive paper, conductive so that it conducts electricity, but then also resistive enough so that it won't short out um, my battery that I connected as a power supply. And what I did is I have here 2 points, and these are actually tacks in 2 locations. And I put those on the conductive paper onto a piece of corkboard, like the kit describes. My initial attempt was to use these conductive pen, but these conductive pens in our lab have been sitting around for a couple of years, and they have dried out apparently, and so they no longer work. And so I had to come up with Plan B, and I thought, well, okay, yeah, we'll just stick the pins in, and they work fine. But it was funny, the instructions really didn't specify using the pins, it seems. Now, one limitation here, all I did was 2-point charges. It would be interesting indeed to use 2 plates and look at the mapping, the potentials around those 2 plates. And you could do that. Just small strips of metal, it seems, would work. Just being set on the conductive paper. Wires, I was thinking maybe you could use. Aluminum foil. So I haven't explored much with that, but I definitely will in the future, and I'm looking to use this activity with my students in the next quarter. Probably I'll get to it. So that was interesting. Now, one thing, using the program that was offered to us on Excel. So here we have this. This is my 3-dimensional chart of my potential. And so this doesn't seem to be very elucidating. My data worked out fine, it seems. I included all of the perimeter cells, the voltage around the perimeter cells, also the interior cells, and then, went ahead and made up this diagram, this chart of voltages. One issue or one thing I noticed is that, okay, well, we've got here, I used a 9-volt battery as a power supply. I connected it with leads to the tacks, my 2-point charges. So here's one tack, and this was at 9.4 volts. I guess that's volts. Joules per coulomb anyway. And so that's one, that makes sense. The other one should have read 0 when I attached both leads to the other one. And the other one would be 5 in from there. Yeah, so I'm only getting 1.4, or I'm getting 1.4 volts for that, the ground electrode, which on my voltmeter read 0, which makes sense because that's the lowest potential there is. That was sort of my ground level. If we make an analogy to gravitational stored energy. So I guess it just took that value. That value was not directly measured. That value was estimated by the surrounding cells. And so, I thought that was interesting. I guess this is, an estimation more or less of some cells that were not directly measured. So anyway, that was sort of intriguing. And then the resulting chart, like I had said, resulted in this. Now, originally, this scale here on the vertical axis was reading up to 3 joules per coulomb per potential. And so that really didn't work with my data because my data um, varied from anywhere between 1.4 um, volts and 9.4 volts. So I had to change my scale on my axis here. And I did that, but that it never resulted in a very dynamic and high resolution type of graph. Now, one thing when I went and read through the teacher notes for Unit 2 is they described this activity, mapping electric potential, and they suggested using a water bath, basically, that was conductive, that conducted electricity, and you could measure various potentials between and around, plates or points that were hooked up to a power supply. And they also suggested this Science First kit, which is just what I did. I didn't use a power supply; I just used 9-volt battery. Well, I use a power supply, but just a 9-volt battery rather than a dynamic power supply or variable. And so the post lab discussion here shows us a 3-dimensional graph of what the potential would look like around 2-point charges. And this is what I was expecting. And this is what seemed to starting to be produced in my graph initially when I was just mapping some initial points. But I don't know, something seemed to change once I mapped all the points. Um, anyway, these different shaded areas suggest equipotential regions, like the yellow, for example. So all along the yellow is analogous to like a bleacher. And so you're not changing your potential along this section, but rather across the equipotential lines or along the electric field lines. And so anyway, it'd be great to sort of do a little more problem solving to try to figure out what's going on in this situation, because these graphs they'd be awesome to produce with the students, because this is great analogy to uh, like a topographic map. Now I'm not sure how much depth I would go into with the topographic map. I know there's a couple activities suggested um, on the teacher notes, and I know David, you suggested the topographic map activity maybe with a model of a mountain, and then using different water levels and mapping out topographic contour lines, um, and then making a topographic map. But I would definitely do some lead in with that. But this is a wonderful way to look at how the potential changes as you go across the landscape around charges.